So hello students, okay, we are going to study what? Bond parameters, isn't it today? So first bond parameter which we are going to study is bond length. Okay, when I say bond length, picture becomes clear in your brain, isn't it? Length, some distance is there, bond, you know the bond is being formed in order to become stable. So here from where the bond is formed, the distance between it, okay, is what? The bond length. So how we will define it? Okay, it is the equilibrium distance between the nuclei of the two bonded atoms. It means if the two atoms are bonded, what happens? The distance between their radii between these two atoms are known as what? Bond length. Okay, basically we are studying about bond length in terms of covalent radius and van der Waals radius. Okay, these two terms are familiar with you in chapter 3 which I have taught, okay, periodic classification of elements. Okay, so covalent radius, do you remember what is covalent radius? It is the internuclear, half the internuclear distance between the bonded atoms. Okay, so here if I am explaining it or describing it, how we are going to say it is the radius of an atom's core which is in contact with the core of the adjacent atom which is what? Bonded. Okay, so here you can see, for example, I have taken here 2. Okay, you can see if I want to say about the covalent radius, it is the half the internuclear distance. So this is the nucleus of the atom, this is nucleus of another atom. So half the internuclear distance, it is Ra, and here half it is Rb. Okay, so now here in this you are seeing if this and this Ra plus Ra, this gives about, which tells about what? The bond length of that chemical bond. Okay, so now the van der Waals radius. Okay, here we are not seeing the atoms, we are seeing what? The molecules which are already bonded together, and the two molecules are again bonded by the forces. Okay, so here you can see here in this molecule, okay, two atoms are there. Here I've said about you about the covalent radius, I've explained you also about covalent radius. Suppose this is the covalent radius of this atom, this is the covalent radius of this, okay, and another molecule also you can see over here, that like that only covalent radius can be taken out. But here van der Waals radius is what? Actually these two molecules, okay, here the distance between this and this nuclei and this nuclei, between the two different molecules nuclei, okay, it is the half the internuclear distance over here, half the distance over here which is being calculated. Then also we see what? The van der Waals radius is more than the covalent radius, because you can see over here, if I say this is the van der Waals radius, okay, so you can see the increased length, because here this van der Waals radius is formed between two molecules, not between two atoms. Okay, now the next parameter which we are going to study is what? Bond angle. Okay, so bond angle, when you hear this word bond angle, you know what is angle, you know what is bond, isn't it? So what is bond angle? It is the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or a complex ion. Okay, so let us study this with the example of H2O, this definition, what it is trying to say. Okay, so what is this actually? When H2O is formed, okay, there are bond formation, isn't it? Here hydrogen is being bonded with oxygen, here also hydrogen is being bonded with oxygen. Oxygen is what? The central atom, okay, containing how many? 6 valence electrons. How many valence electrons are there in hydrogen? Only 1, forming a covalent bond, isn't it? So here you are seeing what? Here the central atom, okay, the bonding pair electrons are present over here and the lone pair electrons are also present over here. Okay, so what does this bonding pair electrons, how does it form, and when we draw the lines we get the angle, okay, and that is known as what? Bond angle. Here you are seeing, here also bonded, here also bonded, okay, so it forms a geometry, thereby forming a angle and known as what? Bond angle. Okay, this bond angle speciality is that it can also determine the shape of the molecule. You can see over here this bonded pair of electrons. When the geometry is made, you can see that it gets a shape, like here water is getting a bent shape. Okay. Now coming to bond enthalpy. Okay, so what is this bond enthalpy? Okay, so it is the amount of energy. What it is? It is the amount of energy to break 1 mole of a bond of a particular type between two atoms which are in gaseous state. Okay, so here if we want to understand this definition, we have understood this is a simple one only. It is just what? It is the energy required to break the 1 mole of bond, okay, which is between the two atoms in the gaseous state. For example, if we are taking hydrogen, it is present in the gaseous state, isn't it? This hydrogen, okay. And if you want to try to break it, it breaks into hydrogen atom and hydrogen atom, okay. But yes, here we need tremendous amount of energy to break it, okay. And that energy which we require to break this hydrogen molecule is 435.8 kilojoule per mole, which is a big value, okay. So this is what the bond enthalpy of what? Hydrogen gas molecule. Okay, so here, if this we are talking about the hydrogen molecule, only two atoms are there. But yes, if we talk about like water, so what we will be taking out? We will be taking out the average bond enthalpy or the mean bond enthalpy. Okay, for polyatomic molecules, we need to calculate the mean or the average bond enthalpy. And how it is calculated? You can see the bond enthalpy of 1 and bond enthalpy of 2 upon 2. This I am writing it for water because water breaks into what? If I am writing H2O, it breaks into what? H plus ions plus OH minus ions. Okay, now here we need to break this also, OH minus ions. Naturally, here two atoms are present divided by 2 and bond enthalpy of 1 and bond enthalpy of 2. If there are 3, beta, you will be using 3 over here plus BE 3 upon 3, okay. It goes on how much atoms are there which are participating in breaking and then by giving the bond enthalpy, and that is, if we are taking of the polyatomic ion, it is the average bond enthalpy. Now coming to the next bond parameter, that is the bond order, okay. Here we had seen that yes, what? This Lewis, a scientist, isn't it? He explained the covalent bond, okay, and he said about what? Bond order. So what is this bond order? It is the number of bonds between the two atoms in the molecules. So now it becomes easy. What is bond order? It is the number of these bonds between the two atoms, isn't it, in the molecules. So now let us see it. How it comes actually, how it is calculated, how it is said, how bond order can be explained with help of examples I am giving you right now. Okay, so see, first example I have taken of hydrogen molecule, second of oxygen and third of nitrogen molecule. Okay, so when we see about the hydrogen molecule, how many shared pairs of electrons are there? Only one, isn't it? So its bond order becomes what? 1. When we talk about oxygen molecule, you know how many shared pairs of electrons are there? How many? It is only 2, isn't it? So bond order becomes 2. When we talk about N2, okay, so N2 what? And you can see over here, what is formed? Triple bond is formed, isn't it? So here, what will be the bond order? 3, isn't it? So, but here in surprisingly, what do we see in N2? Which has got the bond order of 3 and 3 shared pair electrons are there. We see in that, here you can see its bond enthalpy 946 kilojoule per mole. This is the highest enthalpy for a diatomic molecule. Okay, so this, what does it convey to us? It is conveying what? That this nitrogen molecule is too stable because it has got the what? The highest what bond enthalpy. It does not want to break at all. Okay, and if it does not want to break, it is difficult to break. Tremendous amount of energy should be provided to break. Naturally, what happens? It shows that this nitrogen molecule is very, very stable. Okay, so now, this, when we talk about the bond enthalpy for a diatomic, okay, molecule 3, it has the bond enthalpy, the bond order of 3, it means it is very stable in nature. Now, coming to the isoelectronic molecules or ions. Okay, isoelectronic molecules are those molecules which consists of same number of what the electrons, okay, in its ionic form, because they are in different elements, isn't it? So these, when we are seeing about isoelectronic molecules or the ions, if we are saying, they have got identical bond order. For example, if we are talking about F2, this is a molecule of what? Fluorine, F2. And when we are talking about O2, 2 minus, okay, here when we are talking about the electrons, what happens? It is similar, okay, and that is what? 1. When we are talking about N2CO, NO plus, okay, what do we see? Having same what? This isoelectronic ions, and that the value of is what? How much? 3. So, if bond order is more, bond enthalpy will be more. We have seen over here 1, 2 and 3. Here this is the highest bond order. Bond enthalpy also highest, isn't it? But what happens if it is having the highest bond order and its enthalpy is also highest? What will happen? It will not want to give out the other bonded atom. Naturally, what will happen now? The bond length will become less, or it will be decreased. Okay, so here if we are talking in a comparable form, if you are seeing this 3 molecules which we have taken, for example, N2 has the highest bond order, thereby having the highest bond enthalpy, but its bond length will be the least among hydrogen, oxygen. Okay, and if we talk about oxygen comparative to hydrogen, the bond order and bond enthalpy will be more and the bond length will be less. And so here, whose bond length is the least? It is of hydrogen molecule. Okay, so bond enthalpy will also be least, but the bond length will be more. So next bond parameter is the resonance structure. So what is this resonance structure? Actually, when we are talking about the Lewis structure, when the ozone molecule is represented, okay, it is by this structure or by this structure. Okay, if it is a single bond, naturally the bond length will be more. I have written here for 148 picometer. Okay, yes, if it is a double bond, naturally it will be less than that, and it is 121 picometer. Likewise here also, if it exists in this form, it is 121 picometer for double bond and single bond 148 picometer, because single bond has got more bond length. Okay, I have explained you right now. So when we are seeing these structures, these two structures are known as what? Canonical structures or the resonating structures. Okay, it is being said that yes, it exists in the equilibrium form, but nothing of that sort is there. Okay, there is no thing that it exists in this form or it exists in this form. Okay, and they are in the equilibrium form. Okay, but yes, here when we found it experimentally, the scientists found it experimentally, they could find what? That the bond length which should be 148 picometer and 121 picometer, now the bond length which is coming for the same is what? 128 picometer. Okay, so this is what called the hybrid structure, which is in between these two structures. Okay, so this single Lewis structure could not describe, okay, a molecule accurately. Okay, so what happened? Because of that, something which is in between that will be followed. How it will be followed? Here, what should be same? Okay, the energy, the position of the nuclei, the bonding and the non-bonding pair of electrons. Okay, these should be similar, thereby forming a hybrid structure. Okay, so this hybrid structure describes the molecule accurately. But when we are saying that yes, it is existing, if you want to see a single structure, no. Okay, because this is going on so fast that you can't say that yes, we are getting such a shape at that moment. Okay, so this is all about what? The resonance structure. Here energy is also the least from these two. Okay, this hybrid structure. So this is more stable in nature. So next bond parameter is polarity of bonds. Okay, so if you are talking about an ideal situation, it means a compound is 100% ionic, forming ionic bond, or 100% forming what? Covalent bond. But in reality, when we see that, it doesn't happen. Okay, no ionic bond, covalent bond is totally perfect and is having an ideal situation. This I am saying why? Because where the bond is being formed, it depends upon the elements where the electrons are being shared more or less. Okay, so if we are talking about that, see, first is of H2O2 and Cl2. We are saying that this is non-polar covalent compound. Why we are saying it is a non-polar covalent compound? Okay, here actually what happens, here the electrons are shared between hydrogen and hydrogen, isn't it? It is shared between hydrogen and hydrogen. Naturally, this is identical, no polarity is there, and as the result what happens? These are what? Non-polar covalent compounds. We can't say that this hydrogen is a more negative, or this is more negative, or this is a positive, or this is a positive. We can't differentiate that. Okay, so that type of molecules are known as what? Non-polar covalent. Okay, molecules. Now, but when we are talking about HF, hydrogen fluoride, okay, we say it is a polar covalent compound. Okay, why do we say it is a polar covalent compound? Actually, what happens when we are talking about hydrogen and we are talking about fluorine? Fluorine is more electronegative in nature, and naturally what will happen? It will try to take the electrons towards itself, naturally becoming what? A partially negative in nature and this partially positive in nature, thereby forming a what? A polar covalent compound or polar covalent bond. Okay, now, so how do we calculate this polarity? Okay, here it is represented as what? Mu. Okay, that is equal to what? Charge into the distance of separation. Okay, so here we are seeing that this is expressed in terms of what? Capital D. Capital D means what? Debye. Okay, so 1 debye is equal to 3.33 into 10 to the power minus 30 coulomb meter. This has come from charge and this has come from what? Distance. So its unit becomes what? Coulomb meter. Okay, now let us see with some examples. Okay, like hydrogen fluoride. If we are saying how do we represent this dipole, okay, or polarity, we make it a arrow in case of physics, but in case of chemistry we just cut it off over here. Okay, so here what happens, here naturally this fluorine is more electronegative in nature, so whole polarity will be towards what? Fluorine. Okay, now if we are taking the water molecule, it is bonded to hydrogen, oxygen is bonded to hydrogen. Naturally oxygen is more electronegative in nature, so what will happen? The polarity will be towards oxygen, isn't it? And as the result, net dipole moment will be what? Towards what? Oxygen. Take beryllium difluoride. Here we are saying this fluorine, net charge towards what? Fluorine. Here net charge towards fluorine. Naturally this and this will cancel and the dipole moment will become what? 0, or the polarity will become 0. Here you can see this boron trifluoride, 3 fluorine, all taking the electrons towards itself, showing polarity towards itself. Naturally it will cancel up each other and the value of mu becomes what? 0. Now coming to what is this? NH3, ammonia. Okay, here lone pair of electrons are present, and yes, here shared pairs are also present, which are being shared with what? Hydrogen. Here you will see what? Nitrogen is more negative in nature. Naturally, the dipole will be towards nitrogen. The polarity will be towards nitrogen. But here lone pairs are also present. Okay, so here it will be upwards. what happens? So net polarity will be in the upward direction. Okay. Now here it is what? Oxygen trifluoride. Sorry, not oxygen trifluoride. Next example is of nitrogen trifluoride. Okay. So here also lone pair of electrons are present. Okay. 3 fluorine. Okay. Naturally fluorine more electronegative in nature. So what will happen? The net polarity will be towards fluorine, more electronegative than nitrogen. Okay. So, but here lone pairs are also present, na, electrons on nitrogen. Naturally this will show the polarity towards upward direction, but here fluorine, it is towards the downward, and the net 3 fluorine as so the net polarity will be in the downward direction. And this is how we explain the polarity of bonds. So this is all for today, students. Hope you might have understood it. Okay. Good day. Take care.